Welcome to the first session of the day here at the DevOps track at reInvent. My name is aws-reinvent. I'm going to be presenting today with Brian Troutwine here from AdRoll, focusing on how the AdRoll team moved from operating based on sort of by gut to monitoring based on to operating based on data, making decisions in their pipeline based on data. Some of the challenges in monitoring as you're moving into dynamic infrastructure and the like. Okay, so my name's Ivan Rabinovich. As I mentioned, I lead the evangelism and community teams at Datadog. Prior to my time at Datadog, I was an AWS user, much like the rest of you, working for companies like Uyala and Edmunds, building monitoring tooling and infrastructure automation tooling. So definitely have a number of years with that fun. You may have seen me here last year at reInvent chatting about, in the storage track, talking about our use of CloudFront and S3 for serving videos. So I mentioned Datadog. So just to give you a quick overview of who we are and what the relevance is. This is not a sales pitch, so I won't spend too much time on it. You should totally come by our booth at the expo floor and learn more about that later today. But we like to think of ourselves as monitoring for modern applications. Think of systems and applications running in the cloud, dynamic infrastructure, microservices, containers, all of those things that you're here at reInvent to learn about this week. Those are the things that we strive to monitor. Think of us as time series storage for your metrics and events. So any type of event or metric you'd like to put into us, we can help you alert on, monitor on trends, let you slice and dice that data in any number of ways, and we'll go into that in a little bit later here. And then hundreds of built-in integrations. So we're here at reInvent. I'll mention the AWS specific ones. So if you want to pull in your CloudWatch data, things like getting metrics off your EC2 instances, ELBs, the EC2 container service, and much more. And so you're going to be able to slice and dice all that data together and really get some great insight into your infrastructure. But again, as I said, this is not a sales pitch, so you should come by the Datadog booth for a demo later today, and we can show that to you with a live demo. So as I mentioned, we're here in the DevOps track, so let's just really quickly do a refresher on what DevOps is and why that's important. John Willis and Damon Edwards a few years back coined an acronym that kind of speaks to the themes that are behind the DevOps movement. Culture, automation, metrics, and sharing. Some people say that as measurements at times, but you get the gist. Culture is really about people and process first. So it doesn't matter, all of the other things that Brian and I are going to talk about in today's session, they're important. Automation is important, building all your tooling is important, but if you don't have the right people in place, you don't have the right culture in place, you're not working together collaboratively, doesn't matter what tools you have in place. So that's really the first thing you want to focus on, is building a collaborative team where folks can succeed together. Automation that's the core of why a lot of you guys are here this week at reInvent. This is about scaling with code rather than with people. That could mean using a cloud provider like Amazon so that you don't have an army of folks in a data center racking and stacking servers. It could mean automating your deployments with things like Chef or Ansible or Puppet or any of the other tooling. But really, it's about, as I said, about scaling with code rather than with people, so that as the work increases, you don't have to double, triple, quadruple your team at the same rate. And then there's metrics, which is the core of this talk here today. If you don't measure, you can't tell if you're getting better. And that's true in the cloud as well as anywhere else. And that could be hard metrics like how your servers are performing and how much CPU they're using, requests per second. It also could just be how many outages you're having in a given period of time, or how many story points you're moving through in a sprint. It's really just about tracking a number, deciding where you want to be, and then moving towards that direction. And then finally, sharing. This sort of loops back into the culture piece, but again, all of these tools that you built, they're way more effective if you're sharing that data between your team members and if you're working together collaboratively. So if you have an incident, maybe you're all looking at the same graphs rather than one team having a certain set of graphs, another team have a different set of graphs, and now you're sort of maybe pointing fingers at each other, whatever. You want to be having blameless postmortems. You want to be in a situation where you're all ready to work together. You see the problem as the issue that you're tackling together, whether it be a technical problem you're trying to solve or an incident that you're experiencing, and not some other team on the other side of some wall. So at the end of the day, that's sort of a quick overview of CAMs and what DevOps is. And as I said, we're going to focus on the metrics and sharing piece today. both in my section of the talk as well as later on with Brian. So we're all here at reInvent. You're all excited about the cloud. You've been in the cloud probably for some period of time because you're here at the conference. And everything's awesome. Like you've got the scale that you're looking for. You're able to automate all of these workflows that you have. You're not running into resource contention because you're now constrained by your credit card, not by the four walls of your data center. This is great, right? I mean, we've got things like auto-scaling in place, where based on the amount of work that came in, all of a sudden your nodes are going to spin up or spin down. Things like container orchestration, so that you can deploy consistent services and workloads out into production, whether you're using ECS or Kubernetes or Mesos, things like that. Infinite storage, right? You have things like S3. You want to upload a couple terabytes worth of files? No worries. You don't have to worry about putting some drive somewhere. So this is really the dream of probably most operations folks, right? You're not worrying about these limits. But we're trusting the cloud to do a lot for us, and we're trusting our automation to do a lot for us. And the real question is, how do we know when that's being successful, and how do we know when that's failing? How do we tell the health of both of our organization, as well as the applications we're looking at? Again, we talked about earlier about the importance of metrics for tracking towards success. So the first thing our first strategy, of course, like anything we do in anywhere else in our organization, and whether it's on-prem in the cloud, we say, if it moves, monitor it. And we probably also say, if it moves, alert on it, right? Well, we're going to pick some arbitrary thresholds based on our past experience, set those limits, and say, wake me up in the middle of the night if X happens. Graph that, hope for the best. And so as we go to do that, our first thing to do is probably going to open up our bag of tricks and say, these are the tools I know, these are the monitoring strategies I've used, I'm going to reuse those in the cloud with my dynamic infrastructure. And so how does that fit in? The reality is, those were the best tools of a decade ago, right? Just like they're now relics. Those are the strategies of a decade ago. They don't fit in. They were built for a situation where things were not changing constantly, and that's not where we are today, and that's sort of opposed to what you've done as you're moving into the cloud. But we'll dive into a little bit more into the why. So the first thing is, most of that monitoring is host-centric. You've picked a certain host, you've decided it's your Nginx host or your Redis host or your Cassandra host, and you're going to monitor it for that, and you're going to monitor it for its lifetime. The thing is, we've moved into a world where we're no longer thinking of our servers as pets. They're now cattle, and we're culling them and spinning more up and down and replacing them fairly regularly based on workloads. And so we want to be able to track a lot of those metrics and a lot of that state across hosts rather than on specific hosts that may not exist in a minute, let alone in a week. So I don't mean to pick on Nagios here. I love I've used Nagios for a number of years. It's just sort of a canonical thing that we've all, probably everybody in the room has used at one point or another. So it's a good example to work with. So again, the other piece there is most of the tools that we've worked with in the past are likely, they rely on static configurations. So even if you've gone through the effort to chef that up or puppet that up and you're in a situation where that's generated dynamically, a lot of what you've done is you're sort of tricking a static system and causing it to pretend to be dynamic. And as things are changing every second or every minute, you want to be in a situation where your systems can respond in kind. And so if you can't, you end up in a situation like this, right? We've got a sort of Nagios config block here that we've either handcrafted or generated. We're telling it to monitor our favorite host for a given service, except that service is part of an auto-scaling group. And so what happens? Your pager is going off every 5 minutes as you scale up and down, telling you that things are not working. Finally, a lot of the tools that we're looking at and a lot of the processes that we're looking at are really focused on resources. At the end of the day, your customers are not particularly excited about whether or not your CPU load is high, whether you had a network spike. What they care about is did the service that they came to your website or to your API for, is that functioning, or are you returning what they want? And so a lot of the monitoring that we worked with in the past, whether it's because of our strategies or because of our tools, you tend to be focused on those resources rather than maybe that work output. And then finally, as we're looking at this, we're pulling in data nowadays from so many different systems. You're relying on third parties for APIs. You're relying on back-end services from AWS. We're talking about things like, we talked about auto-scaling groups. You want to show events from that. We have CloudWatch data. We have ELBs. You want to maybe look at the latency of requests coming in there versus the latency that your requests are seeing at the application level. So you want to be able to show that all together, and a lot of the strategies we've used in the past maybe have you looking at 10 different dashboards and in your mind trying to come up with a mental model of how they fit together. So let's define those pieces. I said, we were talking a little bit about work metrics. We were talking a little about resource metrics, what they are, and why they're important. I'm going to just do a quick TLDR on some of these pieces, but if you're interested, there's a blog post that we linked to in the slides here, as well as my colleague Matt Williams will be giving a talk tomorrow one room over, where he does a whole hour session on the strategies behind these, identifying these metrics and where to use them. So work metrics, these are the pieces that we were talking about earlier. This is what your customers care about. Think of it, if you're in a factory and you have an assembly line, you're spitting out cars, the car is the work that you are doing, or the widget that you are building is the work you are doing. If you're in a web application, it's likely requests per second is your throughput. Successes is when you return a 200. Errors would be the rate at which you're returning maybe 500s or 400s, things of that nature, and the like. So those are the pieces that you really care about. This is what customers are paying you to do. Resource metrics, on the other hand, these are the things that go into producing that work. So we talked about CPU utilization or I/O. These are the resources that are consumed for making that work happen. And again, you're interested in those as for context or information about how your application is performing, but they're not as key to the success of your event, of your work. They're not necessarily what you want to alert on. And events are changes in your infrastructure. Did you do a code deployment, scaling, et cetera. And so as you're looking at this, what you want to be focused on is paging on those symptoms, paging on when you're not being successful, and then using those other metrics to diagnose. So you're going to start to look at your work metrics, see how they tie into your resources, continue to dive down, look for correlation to those events that you mentioned. And so you're just going to kind of recurse down that stack. And then you want to be looking at situations where you can ask questions across your infrastructure. Things like, again, aggregates are really what matter, not necessarily individual hosts. You want to express your monitors as questions. What was the average response time across all of my Nginx hosts? Was it over 500 milliseconds? Alert me. Maybe are we less than the number I want? Alert me. Things like that. And then you want to be able to mash up all that data for a 360-degree view. So just a quick kind of example of this. In this situation, we're looking at I/O across all of our Nginx hosts, broken up by availability zone. You want to be able to ask questions like that and say, maybe is EC2 having an event right now in US East 1B? Is that why my I/O has spiked? Or maybe there's some other component in my topology in that particular availability zone that's important. And so you're going to want to look at that, mash that up with a lot of the different metrics that we're talking about, and start to build dashboards like these, where you can take your application metrics, put those alongside your resource metrics, and start to build a view of those. And so with that, I want to hand off to Brian, who's going to dive into how they did that at Adderall. So you got to click on the slide there. I don't know what's going on.
It's fair enough. Hi, everyone. So I am a senior software engineer at Adderall. I'm just going to confirm that this clicker is dead. It is, in fact, beastly dead. My particular jam is I really like things that are vaguely managed disasters, so computers are awesome. So I work on the real-time bidding project at Adderall. Adderall is an ad tech company. Real-time bidding is a thing where you see an ad on the web, and it seems to follow you around the web. That is real-time bidding. They don't actually exist when the web page is rendered. There is a little bit of JavaScript, and then there's an auction that occurs through an exchange. So the exchanges are people like Google, Facebook, et cetera, and they signal out to various different companies. One of those companies is Adderall, and I work on the product that catches the exchange, the auction notification, and then responds back with a price or with a no bid. So I'm going to try this again. Nope. That's OK. It can stay there. I got nothing. Oh, there we go. Okay, so the problem domain for real-time bidding is very interesting. It's low latency. So human perception is about 1/10 of a second. If a thing happens in less than 1/10 of a second, we kind of can't notice it. Some people, especially young people, will notice a flash, but people my age and older, they don't really see that. So our system has to be sure when we get a notification that an auction is available, that we respond in less than 1/10 of a second. And that includes network travel time on either side, so we actually have less than 1/10 of a second. It's a firm real-time system. So we've sort of changed the meaning of real-time in the last little bit to say, like, oh, you get a thing and then you respond pretty quickly. That's not actually what I mean there. There is a jargon term, real-time, that was coined quite a bit a while ago. It means that every computation that you have has some implicit clock. It has some implicit deadline. And there are 3 gradients of real-time. A soft real-time system is one in which you go past the deadline and your computation still has value. You can still use it. A hard real-time system is one in which you go past the deadline and something, your computation has no value, and also something is now on fire, or there is someone who is now a piece of paste, like against the inside of an aircraft frame. A firm real-time system is less frightening than hard real-time. You go past the post and your computation has no value, but nobody dies. So there's no catastrophe associated with a firm real-time system. So in our system, when we go past the post, we lose the ability to give an ad, and in a single event, no one cries. Like, that is just not a big deal. If we accumulate too many of those, bad things happen, but I will touch on that. It's highly concurrent. The system does approximately 2 million transactions per second at peak. It's actually gotten so large that we have stopped aggregating over an entire day. We have that number, but it's just not valuable. It's too big to conceive of. And we're global, and we're 24/7. We can't shut down, ever. So this thing has to just keep rolling, and that has interesting consequences. The sort of analogous thing in the world is high-frequency trading. And high-frequency trading is a little bit different because if you're the first one there, you are the winner, whereas we have a set block of time, but they get to shut off after 14 hours, and we have to keep running. So if you know high-frequency trading, that's basically the same modus operandi, except for ads on the internet instead of liquidity in an economy. Okay, so in the early days of the ad real-time bidding project, we could use our intuition. The system was small enough and simple enough that we could sort of hold the context of it in our minds. When we sort of discussed it, it was doing simple enough things that everyone could be a domain expert on everything about it. And the total number of requests coming into the system was relatively small. And human intuition with regard to systems is real good when it's human-sized, because we are sort of these macro creatures that are relatively slow, and if you have a system that has relatively few things coming into it, it fits into our intuition. And the impact of mistakes was minor. The business relies on the real-time bidding system, but as we were sort of chugging along, there was less reliance on the effective use of the real-time bidder, and there was less traffic coming into the system, so the thing going offline just wasn't as bad. And we could be reasonably confident that when we made a change to the system, our mental model of the system's behavior was accurate. So we could sort of reason about the state of the system without necessarily having empirical data, because it was small enough and compact enough to fit into our intuition, to fit into our expectations of how it would work. The trouble with a complex system, as you add more and more and you get more ambitious, is that its behavior and practice gets away from you pretty fast. Human intuition runs out real quick. And the trick there is when you're building a vaguely managed disaster like a software system, you don't necessarily know that you've stepped over this line. It's sort of a gradient from, I got this, to, oh no. So, we need to address this. We need to start getting intuition back. We need to start building better models. So, the first approach that we took was to batch process our logs generated by individual bidders. So the bidders have a relatively large data stream, and we would just chug that out into S3, and then we would have another team that would pick those up and then churn through them, and they would get us a sense of how the bidders were working in practice. And The pros of that was we were already doing this. That's how we do billing. It's how we do a lot of different things. So we already have this infrastructure in place. So we're just able to sort of leverage this. And as a result, it's very simple to implement, which is fantastic, because we were able to get a sense of how the bidders were working with relatively low effort and without having to build our own data processing pipeline, because there's a group that does that. And it's relatively straightforward to conceive of how to instrument a bidder just through logging, because everybody here in this room has probably done print debugging, and logging is just print debugging, but a little more formalized. So the batch processing wasn't a perfect utopia. There's a high update latency to batch processing. So you're kicking out these large logs, and then it goes into a data processing pipeline, and the latency of that could be an hour, a day, and catastrophic errors with the bidder or catastrophic failure of the machine that the bidder is resident on will cause those logs to just get dropped. So if we have an event and that event causes machine death, we have no insight into that event because the machine was not able to take the relatively high latency process of uploading to S3 to completion. And this sort of approach, this sort of high latency update denies impulse experimentation. It denies you the ability to say, what if I tweak a config value? So when we design the bidder system, every new feature is configurable, and we have the ability to change the configuration on the fly. In a batch processing world, you change a value, you wait a day, and then you look, which is real bad for experimenting because you've moved on, the context has slipped out of your mind, so the work that you're capable of doing is less good than it could possibly be. So we needed something better. So our second approach was coarse real-time metrics. We generated metrics in real time, and then we analyzed those. So this was actually pretty effective, and it's an iterative step up from batch processing. So we're able to conceive of how we would do it based on batch processing. We basically just went in, and everywhere we had a log out, we inserted a call to kick out to Graphite at the time. And this proves out the concept. It had clear value once we did it, and it was also relatively simple to implement. I don't know that we did it with it, but I think now I'm probably good enough at sed that I could just sed this thing out. The cons of doing coarse real-time metrics is that you still rely on intuition. You still rely on this I know how the system is behaving, so I know where to put these basically real-time printf statements. And the bidder implementation was suboptimal. It was slow, it was relatively memory intensive, and the dashboards that we had that were catching these, the tool that we were using, they were sort of a one-size-fits-all approach. They were so awkward to build that the person who would add these statements in would then build a dashboard and then just sort of give that to everyone. And the problem with that, when you have someone that builds a dashboard, they are implicitly building a dashboard based on their own mental model of the system, which is different between everyone in the team. And everyone has different needs for visualizing data. So one-size-fits-all dashboarding is a real hard gig. So by this point, the complexity of the system and our ambitions were growing. We added 2 more engineers to the team, so we have more and more need to be able to coordinate on the activity of the bidder, and we have more and more likelihood that a feature will come in that not everybody is a domain expert on. So not everyone will have the same mental model of the system. So now we've built something that is not understandable in totality by a single human. And we were adding more and more people in other departments. So the company was growing very quickly, and the real-time bidder was becoming increasingly fundamental to the company's nature. So more and more people wanted to know about how the bidder was doing, and relatively quickly. So the challenge here is how do we take, we've gone from batch processing and we've gone to coarse real-time metrics, and that clearly has value. It's clearly a step up over batch processing, but how do we take that and make something even better? And because of the defects in coarse real-time metrics, we were making decisions in a knowledge void. We would still sort of have to reason about something with our increasingly flawed mental model, and then just sort of guess and hope that it worked out. So at this point, what we've got is CloudWatch. And CloudWatch is great. It ships with all of your AWS machines, but it reports the basic health of your system. So it's focused on the machine and not necessarily the system that you have built. So where you can indirectly see your system reflected in the basic health of the machine, that's great. But you need application-specific metrics because you have application-specific concerns. So CloudWatch provides the total view of the AWS systems that you're using. Is DynamoDB having a problem? Is S3 having a problem? But again, that's an indirect measure of your system. If your system uses those things, you can sort of reason about it, but we want to get away from having to reason about things and just having, dead, straightforward, stupid, blunt, simple instrumentation of our system. So what we don't have at this point is a detailed view of our system, and increasingly we need one. What we don't have is the ability to explore the information that we have, especially in a high-stress situation. So as our mental model drifted, we kept making goofs, and those goofs have to be worked very quickly with a poor amount of information available to us. And that's real challenging. So the bidders we've implemented in Erlang, I've talked at Erlang Factory about this. If you use Erlang, Exometer is a library that we use, and it solves our Erlang side problem. How do we get cheap, real-time metrics that have sophisticated aggregation? It's incredibly useful. This talk is not about Erlang, but if you are at all interested, Exometer is your library. But getting information out of the bidders is a challenge, or into something that will aggregate and do something sensible with it. And Datadog is the thing that solves our aggregation, our visualization, and our alerting. And all of these are extremely sophisticated and complex things to do. And we shopped around quite a bit. But this is not a sales pitch. But Datadog is real nice in that it integrates with CloudWatch. Our system-specific metrics can then be correlated with the basic health of the system. So we're able to take this indirect thing, and we're able to take this very direct thing, and sort of combine them and do something very, very useful. And this can be done in real time. In effect, basically, it's just the latency of your update interval. So if you kick something out every 15 seconds, you have a time series that updates every 15 seconds. And the very nice thing is this can be done in very high-stress situations. This sort of correlation can be done when everybody's freaking out, when your CTO is yelling across the office, and you can sort of collaborate together. And really interestingly, this can be done by other departments of the business. They have the same structured data that we have, and they can see our dashboards and sort of what we're caring about, and then they can build their own. Datadog makes building dashboards incredibly simple to do and incredibly quick to do. So in the real-time bidding project, each team member has sort of their own group of dashboards, so that the dashboards, they fit into our mental models. And you can see that reflected in other parts of the business because they have a particular mental model of how this thing fits into their world. So now I kind of want to talk about, we're able to do this in high-stress situations, but what does that process look like? So I'm going to walk through different problems that we had. And the first one is really interesting. So it's a timeout spike problem. So I mentioned that the bidder is a real-time system. So in our term is that a single event from the exchange, times out when we don't reply back to the exchange in 100 milliseconds. Depending on the exchange, it can be 60 milliseconds, depending on the region of the world. So we're real concerned about that. In a single event, it's not a problem, but when you have thousands of them, the exchanges will start to limit our traffic. They will believe that we are not capable of servicing it, so they'll cut our traffic down. And that's a problem because we make money on traffic. If we don't have traffic, we don't have money, and if we don't have money, we don't have a business. So, this is one of the very early wins of our sophisticated real-time monitoring with Datadog. We had no idea that we actually had timeout spikes. Our intuition said that we didn't, that we were servicing traffic and that the exchanges thought we were golden, and then we started graphing it. And it might be a little hard to read, I'm not sure, but the peaks there are 5K. So that means that on average, each bidder periodically, in a very suspicious pattern, 5K timeouts, and then it goes back down. So, in a real-time system, you don't necessarily want the highest performance. You want consistent performance. You want to be able to always say that no matter the load, no matter what, everything is nice, flat, and steady. And this is clearly not nice, flat, and steady. And we really, really did not realize that this was happening. We had almost no understanding of how the system actually behaved in practice. So, we start digging into it. And this is the system load. So this is all over a fixed time period, and we start looking at the system load. We ask ourselves, is the exchange just sending us bursty traffic? And there's some random walk around a mean here, but no, they're not. This is nice, flat, consistent. So the system load is normal. There's not a periodic spike in bid requests, so that's one hypothesis gone. So you can sort of see that we're starting to get into this work pattern where we're making hypothesis, and then we have an empirical result, and then we sort of churn on that. So we started looking around, and we start graphing more things, and then we look at the network I/O. So network I/O, there is actually a very suspiciously correlated burst in traffic out from the bidders. So that's real interesting, because whenever you find a correlation, that's something where you can hook a hypothesis to it. So then we start looking around this sort of thing. And not to get too deep into Erlang, but basically the way Erlang works, we have these incredibly cheap processes, but they're not operating system threads. They run on operating system threads, and they're sort of cooperatively multitask across these threads, and they're called the schedulers. And the schedulers, in effect, have a queue on them, and that's called the run queue. So if a scheduler is unable to service its processes, the run queue grows. And the run queue, as it grows, indicates that latency will increase in the system, because for any process, statistically speaking, it'll take longer to come back through. So we chart the run queue. We chart the run queue for all of our scheduler threads, and we notice that there is a correlated spike in the run queue, meaning that the system itself is incapable of servicing traffic in sort of bursts. So that's why we would time out, because you have something that's running on a deadline, and then it's just not able to be computed. So the correlated spikes in the Erlang VM run queue is real interesting, because it means that something is happening with regard to CPU resources, just sort of using our reasoned understanding of how the VM works. So the VM scheduler threads, we lock them to a CPU. So they don't drift around, and they don't have to do context switching. They just own the CPU. It turned out that we actually had a very CPU-intensive background process that kicks on every 20 minutes. And it might have been hard to see, but those peaks occur in 20-minute intervals. The trick was, even though we had pinned a CPU and thought, this is golden, we actually hadn't set up a CPU shield. So the bidder ran cooperatively with all the other processes running on the system. So you have this thread that is pinned to a CPU, and then a high CPU intensity process comes on and kicks that thread off. But it turns out that thread is actually doing real-time things, and you can't kick a real-time thread off. So when it gets kicked off, all the processes back up. And then it comes back on and tries to process, but it's too late, and so everything times out. So that was one of the extreme early wins. And that was sort of something where we could sort of lazily go about it. We were concerned, but it wasn't a disaster. This is one of the first disasters that we had when we had our integration with Datadog going on. For us, failure of bid request traffic is an all-hands problem. It's something that everybody has to look into, because it means the system is not able to do what it's expected to do. It doesn't have the resources that it needs. Without traffic, the bidders can't do anything, because all we do is we just take a bit of traffic and we either say nothing, no bid, or we say money value. So this is a really good day. Relatively, actually, so it says 1 hour there, but that is a multi-day segment. So if you look at the bid requests that come into the system, they have this sort of like up-down curve, tends to peak around 11 o'clock, and then drops at night because there just aren't people that are looking at the web. So this is normal traffic patterns for the real-time bidder. And it's a healthy couple of days worth of traffic. It dips in the night, then it climbs back in the day. This is a disaster. This is a real hard traffic crash. This is over a 4-day period, and you can actually see that this is completely artificial. No humans were involved in doing this, at least not in aggregate. So when you see sharp curves in human-generated data, it's not humans doing it, it's something else. So this is a weekend's worth of traffic lost. We were getting more sophisticated with using Datadog, but we were not good at doing alerting yet. We just didn't know when we came into the office and everything was bad, because we happened to look at the graph. We eventually got better, in part because of things like this. So we confirmed with CloudWatch that the networking of the machines was fine. You could actually get traffic in and out. CloudWatch is the basic health of your system. And we also confirmed that no one had snuck production changes in. We used to play, real fast and loose. We eventually got better at that too. All detail metrics from the VM are acceptable. We went through the usual suspects, or the run queues backed up, et cetera, but none of that. So then we went to the Exchange partner, and we looked at their traffic, and we confirmed that there was a correlated crash on their side. So they're just not sending us traffic. The Exchange has confirmed a drop in traffic from their system. So it's not us that's doing it. We're just not getting anything from them. It turns out that we had hit an implicit Exchange limitation. So we had synced over greater than 2 billion cookies to them, and they had a clause in their implementation that said if it's greater than 2 billion, it has to be wrong. Like, there's no way that anyone could have more than 2 billion cookies. So when that got triggered, they just decided that we were fraudulent and shut us off. They eventually upped that limit. And we became more conscientious about alerting effectively. So that was the big win there. We had nothing to change except our process around how these things get worked out. So sophisticated autoscaling. At high scale, it's very easy to be over-provisioned for your system's load. It's real easy, especially in Amazon, to just say, I don't fully understand the performance implications of the system. Here's $10,000. Real easy, real tempting, especially when it's not your credit card, too. But what's worse is that it's very easy to be under-provisioned for system load. If you're not real careful about it, it's easy to be like, I only need 2 computers. Oh, it turns out I needed 40. So you have to have some way of doing autoscaling, and AWS's autoscaling is real excellent. All CloudWatch alarms and EC2 instances can be pressed into service for autoscaling, and that's great. So, anything that is reflective of the basic health of your system can now be autoscale event. The first thing we did for autoscaling, because we were massively over-provisioned, was to use remaining used idle CPU. So if the bidder was too stressed, it would consume basically all the CPU resource, and then we would just have an alarm, I think at a threshold of 10%, and then we would just kick autoscaling up. So, this was a big win for us, actually. So this is number of bid requests coming into the system, and you can see that it trails down at the end of the day. And as traffic drops off at the end of the day, we need less CPU time to process it, right? I mean, it's real handy for us that the input to the system is reflective in the CPU of the system, because we just have to do something with everything. There's no point where we can drop things on the floor. So there's a nice, fairly linear relationship there. And you can see over that same time period, as traffic drops down, the idle CPU climbs. So we have a strong signal here for autoscaling. We have something that we can do instead of just sort of like, here's a wheelbarrow of money, enjoy that, or we can sort of take our money back at the end of the day. And this was great. When we started doing this, we saved loads of money. We chopped out something like 15% of the number of machines that we needed, especially at night. At night, we would go down to our minimums, and that was super, super effective. The problem was it's an indirect measurement. There's always some nuance that you're going to miss. Your system has a complex behavior, and your system is not just distillable into idle CPU. I mean, unless you're happening to build a space heater that just does, computation, to do that, which we are not building a space heater, though I'm sure the machines kick out a lot of heat. Co-resident subsystems eat into the CPU time. So our bidder is not necessarily just Erlang. There are native components that get shipped along, and they eat up that CPU time. And we don't necessarily want to measure that. We want to measure that in a more direct fashion. So we can't say that Buddha is doing something. Buddha is the name of the bidder. We can't say that Buddha is doing something. We can't say that the native component is doing something, because we've just got one value. CPU consumption carries no information about aberrant system issues. It is just distilled into one value, and it's very indirect. And as you do more sophisticated things in the machine, it gets way too indirect. So, what can you do? The trouble with having just a single metric is, while it's easy to conceive of and it's easy to start with, it's not effective in the long term. The real trick is that CloudWatch doesn't allow you to autoscale on multiple things. Technically you can, but they don't cooperate. You just sort of say like, well, do a thing, and then do a thing, and then do a thing, and you hope they don't collide. So if any of you have ever built control systems, that is the least optimal way of building a control system. So you've only got one signal out. So what do? you distill the performance capability of your system into a single signal. So it's a single signal control system, but you know that you need multiple signals, so you just combine them. So what we did was we just took bid requests, we took timeouts of some of the subsystems, and we took latency metrics, and we summed them, and they're weighted in terms of our concerns about those. And we call that the metadata index. And you can see here that the metadata index is meant to fluctuate between two lines. And so that's where the auto-scaling gets set up at. Bottom line is where you scale down, and top line is where you scale up. Real simple and real effective. The metadata index tracks the load on the bidders. It's just a weighted sum of metrics. So it's very useful to take your sophisticated understanding of the system and just sort of say, like, this is the most important, less important, less important, less important, less important. And as the traffic drops, the metadata index drops because it's largely pegged to bid requests, and indirectly, idle CPU increases. So, we embed this metric index into CloudWatch as a custom metric, and we're able to auto-scale on it. And as soon as it hits CloudWatch, that's us. We're golden. So, as sort of bid requests climb up in the day, indirectly, CPU decreases. We're needing more and more CPU. But it turns out that there's not a great indication in the modern system. But once we start auto-scaling on this metadata index, you can see that as the traffic increases, we're able to sort of keep this thing in parameter, which is a thing that we were unable to do with CPU because it was it fluctuated too much. I mentioned that we had periodic tasks that kick on their high CPU users. So this is a very, very direct measure of the system's performance. And it sort of proved out in the number of EC2 hosts that we use. So you can sort of see that we dive almost all the way down just to 6. Our minimum threshold is 4 for redundancy purposes. And then through the day, even as traffic fluctuates and jitters around, we have these nice, flat, consistent places in the number of instances that we have. So we've been able to remove some sort of jitter from the system, and we've been able to make it more efficient. In fact, this is twice as efficient as CPU idle scaling as that signal. So we need 1/2 the number of machines that we needed previously, and it's been an incredible cost savings. And it's also very valuable for our understanding the system, because instead of saying, well, I don't know, geez, like the CPU, we can say a thing that we know very well is doing a thing that we understand very well. And blue line here is the number of machines we need. Purple line there is the number of machines we needed a week before. So just immediately useful. And sort of the last thing I want to talk about, the advertising industry is fun because on the modern web, there's an incredible number of fraud. There's an incentive to cheat and get people to pay you money for a thing that didn't actually happen. And we see a lot of this, and we've had to become more and more sophisticated as we've detected this at combating fraud. And we knew about certain kinds of fraud that we just accepted. We called it the hot cookie, and it caused a tolerable fault in the bidders. So the bidders are such a large, complex system that it's not correct by design. It is fault tolerant by design. So there are certain low latency errors that occur that we just consider to be acceptable for the time being. In particular, this tolerable fault was to do with our DynamoDB usage. So we store a lot of stuff in DynamoDB. If you have a hot cookie come through, the way DynamoDB works is it hits a single shard, and then it goes over your threshold for that shard, and then you start getting timeouts. Or we refer to them as throttles, but they're just timeouts, because that shard is overloaded. So we were seeing that everything that was co-resident on that shard would now start timing out because you have one fraudulent cookie that's hitting you 100,000 times a second. But we considered that acceptable. We just massively over-provisioned DynamoDB, and we went on our way. And then eventually we wanted to not just give a wheelbarrow of money for that, so we started fixing it. So we built a thing called CookieBouncer, and it blocks bidding on fraudulent hot cookies in real time. It's just a control system, and it's a configurable control system. And our concern here was blocking too much traffic. Like I said, we have to have traffic coming into the system, and we have to be able to service it. And if we block too many legitimate bids through over-aggressive tuning, through saying, like, this cookie can't show up that many times, then we will start to lose money. So we had to have some sort of heuristic for deciding that no human could send us their cookie in too many, some window too many times. But we didn't know what that would be. We had no idea how the system actually behaved in practice. So when we built the CookieBouncer, we had gotten relatively sophisticated with dashboarding, and we had gotten relatively sophisticated with alerting, so we built a dashboard for it. And we introduced the ability to tune this thing in real time on every bidder so that we could roll out CookieBouncer with very conservative settings that basically turned it off, but it was running, and then start adjusting. We could turn it, make it more and more aggressive, and we could keep tabs on the key indicators because we've got very finely detailed real-time metrics, and we can see in real time our configuration changes having an effect on the system. So, I mentioned before in batch processing where we would experiment, and it would be a change, wait 24 hours, make a change, wait for 24 hours. Now it's make a change, wait for 3 minutes, make a change, wait for 3 minutes. So it's very easy for two people to work together and to sort of keep the mental model running and make a very sophisticated product very quickly. So blue line is current, purple line is week before, yellow is month before. These are the total wins that are coming into the system, and in particular, these are the wins that we are considered to be fraudulent in some way. And you can see as we're sort of tuning this thing that they're cranking down and down and down. So it's having an effect, and it's having a very positive effect because all this fraudulent stuff is money lost to our customers. And as we adjusted this thing, we actually thought that it would behave differently in practice. So our reasoning about this system was not very good. But as we adjusted it, we were incredibly surprised at the number of blocked cookies and the percentage of total traffic that was fraudulent. We thought it would maybe be 1% at most. And when we started doing this, we had to convince ourselves that we hadn't introduced a bug somewhere. The percentages were so high and the numbers of blocked cookies were so high that we backed it off. And we reviewed the code even more stringently because it just surprised us. And you can see as we sort of tune this thing up, on the far left-hand side, there is its most conservative settings. It's basically turned off, so it's kicking out my bounce rate, the percentage of cookies that I've seen in the last second that I've bounced, or excuse me, the last 15 minutes, is 0. It's not doing anything. And then we make it a little more aggressive, and a little more aggressive, and a little more aggressive, and you can see these jumps in cookies. The other interesting thing is the cookies aren't distributed evenly through time, so that's why you have these giant spikes, because you'll get 100,000 in a second, and then you'll never see it again. That was another thing we learned. We didn't know how they were distributed. And as the blacklist, as a bidder comes online and starts filling up its blacklist, you can see that it scales up in a very interesting fashion. And this is the same time period, so you can see on the far left-hand side that we're very conservative, we're not doing anything, and then on and on and on. If we had not had Datadog, we wouldn't have been able to do this. This would not have been a thing that we would have been capable of understanding. It radically changed our understanding of the nature of the traffic that came into the system because we had convinced ourselves that the online advertising world was a nicer place. We wanted it to be a nicer place, but it turns out there's just a lot of crap that flows through it. But because we were able to experiment extremely quickly with accuracy, we were able to understand, what the proper tuning parameters were. And I think when we were doing this, we changed the tuning parameters something like 15 times. So if you can imagine, in the old days, that would have taken 15 days, basically 2 work weeks, to sort of fiddle with this thing. But we did this in less than a day. Like, this was the thing we just put together in less than a day. And it was super, super effective. And, the instrumentation sort of speaks for itself. Like, the instrumentation is not just a thing that is a tool for you, it almost becomes another coworker for you, another thing to bounce ideas off of, another thing to put a hypothesis on and get empirical measurements back. And it radically changes the way that you are able to conceive of building complex products, to introduce all of this telemetry and then make reasoned decisions based on that telemetry, not just your sort of Aristotelian ability to believe that there are more teeth in some people than others. And so we have a thing that predicts the average price. As we turn the CookieBouncer on, once we cut the prod out, our average price prediction jumped way up, like just very, very rapidly. And that's another fantastic win for real-time bidding, or real-time telemetry, because we were able to see changes throughout the system as the positive or negative, depending, benefits of a new feature replicate and spread out through the system. And that is incredibly useful because other segments of the business that are concerned about different things are checking our work. They're saying, how did the prediction jump up? Well, we cut out a lot of fraud. Enjoy that. And that is an incredibly useful thing because now your organization is working together internally instead of at loggerheads with one another. And that has been one of the best things about this work, is that everybody gets a chance to work together. And as was mentioned, there is another monitoring strategy, finding signal in the noise. So if you want to know how to build these dashboards without having to do the 8 months of laborious experimentation that we did, they will catch you up real fast. And I would highly suggest you go see it. And thank you, everyone, for coming.